Thanks again for joining us for this webinar. My name is Mike Rayleigh. I am PAC's Director of Engineering. I'll be giving the presentation today. So this presentation does count for AIA credits. And so, make sure you stay here and you've registered through AEC, that registration link, to make sure that you get your credits. Today's presentation, the topic is better design through a deeper understanding of acoustic ratings. So I'm going to talk about the STC and the IIC ratings, two common ratings you've probably heard about. And we have a sort of a wide variety of folks here today. We've got quite a few architects. I think we've got some contractors and folks here, and also a fair number of acoustical consultants. So there's probably some of you on this call who know these STC and IIC ratings far better than I do. But I'll go ahead and talk about them. Hopefully there's some useful information for y'all as well. And I'm also going to talk about two new, fairly new acoustical standards that have come out in the past couple years or so. And those are the HIIC and LIIC standards. I'm going to talk about how those are useful, what they do for us, what they are. So with that, I'll go ahead and get into it. Right, it's just an overview of what I'm going to talk about. So I'm going to talk about the STC and IIC ratings and what are they. I'm going to talk about the difference between lab and field measurements. This is something that comes up. You see it referenced in the building code for acoustical standards for sound isolation and large residential buildings. I'm going to talk about what those differences are. Talk about some myths and misconceptions, things that I've heard, questions that I've gotten a lot over the years. Talk about some of those and how they can lead us astray sometimes. Then I'm going to get a little bit more technical. I'm going to talk about reading the STC and IIC graphs because these single number ratings, the STC and the IIC, they don't tell us the whole story. Right. And so having a little bit better understanding of what goes into those ratings, I think can help all of us better design quieter spaces. I'm going to talk about how they're calculated and some of the shortcomings of them. Right. And then that will lead us into talking about these new ratings, the HIIC and the LIIC, and how they sort of address some of the shortcomings of the IIC rating. And then last but not least, I'm going to talk about methods of improving these ratings, just some sort of general concepts that you can use to apply and how they affect these different ratings. So before we get into this, I just kind of want to sort of set the stage for all of this, talking about these acoustic ratings and code minimums and everything with this quote. With the current level of performance specified by the building code, a large percentage of people are highly annoyed by noises from their neighbors, leading to reduced quality of life and possibly to negative health effects. Right, that negative health effects is a big thing, right? If we're trying to design spaces that are healthy, trying to design healthy indoor environments, right? Noise is a big part of that, and noise can really contribute to our health in a negative way. And so, this quote about the code and it not being high enough, this isn't some, just acoustical consultant saying, hey, everybody needs to do better, pay more attention to noise. This is actually from the International Code Council themselves. This is a supplementary document of theirs, the 2010 Guidelines for Acoustics. And it's a great reference. I've used it as an acoustical consultant as a reference, and I think it's also a great reference for architects and others to look at. So with that, let's get into it and kind of start talking about what these different ratings are and what the difference is between STC and IIC ratings. So first off, STC stands for Sound Transmission Class, and it measures the reduction of airborne sounds. So that's really sounds that start within the air. So we can talk about examples of people talking, TVs, stereos, those sorts of things. And STC ratings apply to both walls and floor ceiling assemblies. You can also have STC ratings for doors, windows, things like that, right? And the way we measure an STC rating is, I've kind of got this very simple sort of schematic layout of a laboratory setup, right? Is we have these two separate spaces, two isolated spaces. We have a sound source in one room. You can see the speaker up there in the upper left corner. We make a bunch of really loud noise in that room. And we'll measure how loud it is in the source room, and then we'll measure how loud it is in the receiving room. And basically the difference between those two, plus some other calculations and things that I'll go into, gives you your STC rating. So it's really just the reduction in noise from this space to this space because of this partition that you put in the middle. IIC stands for impact insulation class, and it measures the reduction of structure-borne sound. So we're talking about sound where it really starts with an interaction with the structure itself. And the IIC ratings only apply to floor ceiling assemblies. And some noise source examples would be footsteps, dragged chairs, dropped objects, your dog running across the floor, their nails on it, my kids jumping up and down, those kinds of things, right? And so we kind of see that illustrated here by this boot on top of the floor ceiling assembly with, somebody in their home office below, right? So the way we actually measure this in the lab is we have a standardized impact source called the tapping machine, and it has these little metal weights on it, and there's either like a cam or sometimes electromagnets that lift those weights up, and then they just free fall. And so you get this tap, 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 tap on the floor, and you just measure how loud it is down below. And you take that measurement of how loud it is below, you do this curve fit thing that I'll show you, and that's how you get an IIC rating. So the laboratory ratings, right? For airborne sound, we have the STC, and for impact sound, we have the IIC. And in the laboratory, we go to great lengths, hopefully, to isolate the two spaces, the source space and the receiving space, so that the dominant transmission path for the sound is through whatever assembly it is that we're trying to evaluate. So when we're doing the measurements in the receiving room, all of the sound that we're really capturing, measuring, is coming through that partition, not through other places in the structure. And so we call those other ways that the sound can travel around our main assembly, those are flanking paths. So we try to control or eliminate as much as possible those flanking paths. So therefore, we're only measuring the sound going through the assembly that we're trying to test. So then the results of that indicate the performance of that assembly independent of the surroundings. In the field, we have different ratings, and we have this whole alphabet soup, right? So for airborne sound, we have sort of 3 different ratings, an ASTC, an NNIC, and an NIC. And I'm not going to go into the differences between all of those and what they mean. Just when you see those, know that they are airborne sound and they're field measurements. And the differences between them really deal with room conditions, sizes of rooms, sizes of partitions, the amount of absorption in the spaces, and those kinds of things. Impact sound, we also have 3 different metrics. We have AIIC, NISR, and ISR. And again, very similar measurement methodologies. The differences is really just in sort of room conditions, site conditions, those kinds of things. So when we do these field measurements, the flanking paths are included in the measurements. So it's measuring the sound through all of the different paths, right, through our assembly, but also through, sidewalls and ducts and, whatever might be going on in our space. So we have the direct sound shown by these sort of teal arrows. And everything's connected, right? In the lab, we sort of isolate these spaces so that they're not connected to each other. But in the real world, everything's structurally connected. So we have all of these other paths. So for a floor ceiling test, we've got the direct sound through the floor ceiling, but we also have sound that could be transmitted through the walls and down into the space below, or even down to the floor and up from that. And there's a whole bunch of different ways that the sound can go. So the results of a field test indicate the performance of the assembly and the surrounding structure. And what that means is that the results are applicable only to the tested assembly. And if you look at the ASTM test standards for these field tests, they say, if you do this test, it's only applicable to this exact situation. Because even if you moved somewhere else in the building, you might have different, circumstances in terms of, how the walls are built. Maybe the units are stacked in one place and they're not stacked in another. And you have all of these different sort of connections and things like that that affect your flanking paths and are going to therefore give you different results. So those are sort of the differences between the lab and the field tests and sort of how we conduct those lab tests. So then the code requirements, right? Within the International Building Code, we have requirements for airborne sound, right? And for structure-borne sound. And the laboratory requirement is a 50. So if you're looking at, a laboratory test report, it's got to be at least above a 50. And for field, it's a 45. And that's the same for both airborne and structure-borne sound. And if you're designing, if you're looking at a space for multifamily, apartments, condos, anything like that, you need to meet both the airborne and structure-borne sound isolation requirements. All right, so now let's get into some of the myths and misconceptions. So the first thing is you can add STC ratings. Like I've had people ask me about this before. Hey, I've got this assembly that's this base assembly that's an STC 35, and then I've got this other thing that tested at a STC 20. Can I just add the two together and get an STC 55? I wish that it were that easy, but unfortunately it's not. So I have an example here. This is standard 2x10 solid wood joist, some bad insulation in the cavity. And in this particular test, there's just a wood subfloor, it's OSB or plywood, and nothing on the ceiling, right? So the joist cavities were exposed to below. And that got an STC 24. And then we kind of take the flip side of this, and we have something where the top side is exposed, and we just have a ceiling. So this is resilient channels and a layer of gypsum board, and that got an STC 27. So can we just add the two, STC 24 plus 27, and get a 51? Hey, this assembly meets our code minimum of 50, right? Well, unfortunately, if you actually just go and test that assembly, you get an STC 49. Now, it's not a huge difference, right? 2 points is not that big of a deal. And I could come up with other examples where you do this sort of addition of different elements of an assembly and you come up with much bigger differences. But I use this one to show how this could, if you tried to do it this way, it could get you into trouble, because just adding the two STC ratings shows, hey, yeah, this thing's going to be above the code minimum of 50. But in actuality, if you tested the assembly as a whole, it's below. And so it's right at that break point. So unfortunately, you just can't add those. You really need something that tests the assembly as a whole, or you need to do a more detailed analysis of what adding or changing these different elements does. So another one that I get a lot is you can add a delta IIC to any assembly. So first off, what's a delta IIC? So we talked about the IIC rating, that's your impact sound, right? So we have the tapping machine, we have a floor ceiling assembly, and then we measure how loud it is down below. The delta IIC test standard specifies, okay, let's take a 6-inch concrete slab, and we're gonna measure our IIC rating on that bare 6-inch concrete slab. So we're gonna tap on it, measure how loud it is down below. And then take the same 6-inch slab and put some flooring on top of it. It might be tile on a rubber underlayment, it might be an LVT or engineered wood with an attached pad, whatever, put flooring on top of it, and then measure the IIC again. And the delta IIC is basically the difference between those two. So it's the improvement that you get from putting flooring on top of a 6-inch concrete slab. So here we have a delta IIC. I think that this is like engineered wood on a 2mm recycled rubber underlayment. And then here we have an assembly, and this already has a pretty high IIC rating. It's got gypsum concrete on an acoustical underlayment. It's got rubber sound isolation clips on the bottom. So can we just take these two, add a delta IIC of 24 to the 62 for the open web truss, and get an IIC 86? That'd be really awesome. But it doesn't work that way. Instead, you get an IIC 68 when you go and you actually test this assembly. And so the thing is, the delta IIC is measured always on a concrete slab. And concrete slabs behave very differently acoustically than do wood open web trusses or wood I joists or steel C joists or any of these other kinds of things, right? So you can't just take a delta IIC and add it to any sort of joist or truss structure. You can add it, it's measured on a 6-inch concrete slab. You could definitely do it for a bare 6-inch slab, and it'll probably work for an 8-inch or 5-inch, 7-inch kind of slabs. You get pretty close. Sort of heavy monolithic structures, but these lightweight joist and truss structures, it doesn't work. Another question that I get a lot is, hey, what's the STC rating for your clips, or what's the IIC rating for this underlayment? The acoustical products themselves, like the ones that are designed to be a part of an assembly, like sound isolation clips, acoustical underlayments, these kinds of things, they don't have their own STC and IIC ratings, because when we do those tests, we're evaluating the assembly as a whole, not the individual elements of it, right? We're producing sound on this one space, and then we're measuring how loud it is in the space below, right? And we have to have something that fills that whole opening between those two rooms in order to run that test. So here we have two different assemblies, the sound isolation clip in them, right? This thing right here is the same for both, but we have two totally different ratings. We have an STC 56 on the left and a 62 on the right. And the difference is just the number of gypsum board layers, but it's the same sound isolation clip and installed in the same way. So the clip itself doesn't have an STC rating. You have to look at the assembly as a whole. All right, so that's kind of the basic overview of the ratings, how they're measured, how we get them, and some of the sort of caveats, pitfalls, myths, and misconceptions around them. So now I'm going to get a little bit deeper, and I'm going to get into actually reading the graphs that you would get in a test report. So if you're, reviewing submittals from a manufacturer, something like that, you're getting acoustical test reports, laboratory test reports. In that, there should be a graph that shows this detailed data, one that kind of looks like what I have here on the right. And that will tell you a lot more information about the performance of the assembly if you sort of understand how to read it. That's what I'm going to go into now. So yeah, the graphs give details of the assembly's performance beyond just the single number STC and IIC ratings. So ISPL stands for impact sound pressure level. It's measured in decibels, and it represents how loud are the impacts in the space below the assembly. So this is for an IIC test, or the field versions, AIIC, all of those things, right? For impact sound, structure-borne sound. TL stands for transmission loss. It's also measured in decibels, and it represents how much does the assembly reduce the noise levels from one side to the other. So it's for airborne sound. On the bottom here, the x-axis, the horizontal axis, we have frequency, which is in hertz. And lower numbers on the left-hand side of the axis are low frequencies. I'm a musician, so I always like to give musical examples. So you can think of lower frequencies as bass, upright bass, bass guitar, right? And the higher numbers are higher frequencies. So you can think of a violin, right? Or another example would be low frequencies would be the rumble of a diesel train engine. And high frequencies would be like the piercing sort of squeal of a fire alarm like this. And that fire alarm, just for reference, like the sort of standard for that I found is at 3,150 hertz, which is the upper range of the IIC frequency range we look at. And you can think of these frequencies along that horizontal axis or the x-axis as sort of like keys on a piano, right? On a piano, each key is a different note, and each note basically is a different frequency. It's a little more complicated than that, I recognize for all of you acousticians on here, but you can basically think about these different frequencies as sort of different notes, different pitches. And bonus points to any of you for identifying the issue with this piano. All right, so the STC and IIC calculation. How do you actually get from these TL or ISPL values a single number? And it's kind of a weird and complicated procedure. It's a little confusing. So hopefully these two little sort of moving things here, animations, that show you how it's calculated, and hopefully this sort of helps understand. So on each of these, we have the actual measured data for the assembly that's here in gray, these gray lines with the dots. So on the left, we have STC, and that's airborne sound. And on the right, we have IIC, that's impact sound. So we start with our measured data that we've gotten from the laboratory or from the field. And then we have this orange curve, which is set within the calculation standards that are developed by ASTM. And we do a curve fit. So basically, we shift this orange curve up and down, and we look at the differences between that curve and the measured values, the gray line. And so for STC calculation, higher transmission loss values are better, right? Because it's more noise reduction, and we want more noise reduction. So anything that's below the orange line, we call a deficiency. And really all that means is that it's just less than this curve. And so you can see in this animation on the left, as we raise the curve up, on the bottom, we get these little bars, and those are the deficiencies. On the right, for an IIC calculation, doing the exact same thing, we have this curve, and we're comparing it to our measured levels, but everything works the opposite way, sort of. Because for IIC, we're measuring how loud it is down below. So the quieter it is, the better. So we want lower ISPL or impact sound pressure level values. So we start shifting the curve down and we see how low we can get that curve before the deficiencies hit these different criteria. And we have two criteria for our deficiencies. So one is we look at the sum of all of those deficiencies. So the total of all those little orange bars down there at the bottom. And that can't exceed 32. We also look at the value of each one of those individual bars. And no single deficiency can exceed 8. And so we have some situations where the total deficiencies is what sets our rating. We hit that, we exceed 32 first, and so we go to that sets our level. And sometimes that 8 dB limit for a single frequency, that sets our rating. And that 8 dB limitation we call the 8 dB rule. And that's something that there's a lot of conversation about these days, and it's a topic for another day. So looking at these graphs, like if it's something that you're not familiar with, when I've presented this to other people that don't have backgrounds in acoustics or in music, looking at that, trying to understand the difference between all these different frequencies and how they sort of all occur at the same time is often sort of complicated for people. And so one thing I've found that has been helpful for people is this is a spectrogram. And right now, if you look at this, this might just seem super complicated. You're like, how is this helpful, Mike? This just confuses me more. The thing is to go to that link down there at the bottom, the amacoustics.com/tools/analyzer, and it's a live spectrogram that you can just play around with on your computer. And so if you spend a little bit of time with this, just get your microphone and start making some weird sounds into it, you'll start to understand a little bit better what's going on. So at the top of this, we have a keyboard. Again, to the left is lower frequencies, and to the right is higher frequencies. So you can think about this as sort of like the x-axis, that horizontal axis on those graphs I just showed you. And down below, we have color code. So this thing shows you the sound levels relative to frequency in time. And red is super loud, black is very quiet. And if you play around with this, you make different sounds, you'll see how they show up at different frequencies. And some sounds will have a very narrow frequency range. You'll see just colors in a little area, and other ones will have a much broader frequency range. And you can play around with different things, like make all the different vowel sounds and see the different frequency content of those. And this can really sort of start you help to understand, and it's a very visual thing, right? Hopefully it helps you understand sort of the different frequency content of different sounds. Bang on your desk, whistle, hum, do vowel sounds, all of these things, and you'll start to see that. So here I have a couple examples. I think this one was just like me, like clicking my fingernails on my desk or something. So it's fairly narrow and it's more high frequency content. And this was maybe pounding my fists on the desk, something like that. So it's much more low frequency, maybe a broader frequency range as well. All right, so now let's get into the shortcomings of the STC rating. So the STC is really designed around speech specifically, and it has a limited frequency range in part because of that. And if we think about the environments that we exist in, where we use STC ratings a lot, apartments, multifamily, condos, those kinds of things is a big one. So speech is certainly an issue there, but also like music, things from people's TVs and stereos and all of that. And that can cover a much broader frequency range than what speech does. So here is one of those graphs again, and it shows you the frequency range that's used in the STC calculation. So it goes from 125 hertz at the low end to 4,000 hertz at the high end. But here's the theoretical range of human hearing, which goes from 20 to 20,000 hertz, right? So here's the STC range. Here's the full range of human hearing. Now, the 20,000 hertz is way, way, way up there, and you lose that high frequency hearing as you age and you listen to music that's too loud. So probably most of us can't hear that high. That doesn't affect things too much. But those low frequencies, you can have, a standard sound bar that can go well below 125 hertz. And if you have a little bit of a home theater system with a subwoofer, it can go down well below 125 hertz. But we don't look at that for the STC rating. And the single number doesn't really tell the whole story, right? It's not looking at this entire frequency range, but it's also not telling us about the shape of that curve necessarily. We do this sort of curve fit that I went into where we compare that gray line to the orange line, but it doesn't when we just see an STC rating, like this wall is an STC 52, it doesn't tell us like, was it controlled by the total deficiencies or was it just like really bad at this one frequency? It doesn't tell us that. We have to go look at this graph to get that information. And again, going back to that quote at the very beginning, the code minimum does not guarantee satisfaction. Like if we're building condominiums and people are expecting high levels of sound isolation between spaces, especially if you have a place where, you know, people are maybe they're downsizing from a single family residence and they're moving into condominiums, they still bring with them that expectation of the sound isolation and the quiet that they had in a single family residence. Well, a condo building is a totally different environment. And the code minimum is not going to give you anywhere near that sort of quiet solitude that you had from a single family residence. All right, so now let's look at the IIC rating, so the impact insulation class. So it's designed around footsteps, and it too has a limited frequency range. So here's the range for the IIC calculation. It goes from 100 hertz to 3,150 hertz on the high end. But again, here's the range of human hearing. And just like with STC, the high frequency stuff, you know, we're not as sensitive to it way up there. Some, you know, probably just can't hear it at all. It's really that low frequency stuff, though, is the thumps and thuds that you hear, especially in lightweight, you know, joist and truss structures. And those can often be the most annoying and disturbing sounds. So again, the single number doesn't tell the whole story. Same sort of thing that we talked about with the STC rating. And again, code minimum does not guarantee satisfaction. And that is even more so the case for the IIC rating than it is for the STC rating, I think. And to give you an example of that, here's a story. This is a paper in the Journal of the Acoustical Society of America back from 1994. And this is a big study that was done that sort of came about because of a class action lawsuit. It was a large luxury condominium building in San Francisco. There was an $80 million class action lawsuit filed against the developers. And one of the big claims in that was annoyance from excessive noise and vibration due to footsteps. And the complaints came from areas with and without carpet. So one of the things that we think about when we look at just like IIC ratings, for instance, any assembly tested with, you know, like broadloom carpet and pad, you know, for this typical residential carpet, usually gets these really high IIC ratings. And we think, okay, we've got this IIC 75 or whatever for this carpet. We're good. That's way above the code minimum of 50. That should be sufficient, right? But here in this case, the complaints were coming from places without carpet, hard surface flooring, that, you know, to be expected, but also places with carpet. And really what was driving that was the thuds and the thumps and the booming. That was the biggest source of the complaints. And you can still get that with carpet. And I think this is a very interesting quote from this paper. It says the IIC rating of a floor system is meaningless with respect to the perception of these low frequency, the thumps and thuds and booms, these low frequency components of footfall noise, because the methodology ignores the frequency spectrum below 100 hertz. Right, I just showed you that graph, and it goes from 100 hertz to 3,150 hertz, but we can hear things well below 100 hertz, and those sounds are important. So one of the things is you can get the same IIC rating for assemblies that behave and therefore sound totally differently. So here on the left, I have the same graph, right? We have frequency on the horizontal axis and the impact sound pressure level, how loud it is, on the y-axis, the vertical axis. So the higher it is up on the graph, the louder it is. All of the different colored lines represent the measured sound levels from one specific assembly. So we had that assembly in the lab, banged on it on top, measured how loud it was down below at this full frequency range, and then we get that graph, right? So each colored line is a different assembly. All of these assemblies have the same IIC rating. But you can see their levels at different frequencies vary all over the place. So here's the IIC range that's used for the IIC rating from 100 to 3,150 hertz. And so at the low end of that range, at 100 hertz, our minimum was 52 and our max was 65. So a 13 dB difference between the loudest and the quietest at 100 hertz. And for reference, a 10 dB change is a doubling in perceived loudness. So at 100 hertz, the loudest assembly here was more than twice as loud as the quietest. On the other end, the highest frequency, 3,150 hertz, the minimum was 5 dB, and the maximum was 45 dB. That's a 40 dB difference. That's a huge, huge difference, right? So we have these massive changes in these assemblies and their frequency content, but they all have the exact same IIC rating. So if we looked at these assemblies just in terms of their IIC rating, we say they're all equivalent. But if you actually were to stand beneath one while somebody walked around on it or you had the tapping machine, they would sound totally different. So to address some of these shortcomings, we have two new standards that have been developed, the HIIC and the LIIC. So these deal with impact sound, right? Structure-borne sound. The HIIC stands for the High Frequency Impact Insulation class. The standard is ASTM E3222, and it deals really with the sort of the clicks and the clacks of impacts, footsteps on a floor. And it just looks at the range from 400 hertz to 3,150 hertz. So you can think of this as like the click of high heel shoes, or like hard soled dress shoes, or a dog's nails on a tile floor, those kinds of things. The LIIC is at the other end. It stands for Low Frequency Impact Insulation class. It's set by ASTM standard E3207, and it deals with the thumps and the thuds that were the big issue in that lawsuit. And it just looks at the frequency range from 50 hertz to 80 hertz. And so if you look at this, you see that orange bar, right? That orange line is the standard frequency range for an IIC rating. So you can see that the HIIC frequency range fits within what we already use for an IIC rating. But the LIIC is outside of that. It goes lower down. And that addresses that issue that Blazier and Dupree said in their standard, or their paper, that the IIC ratings are meaningless for these low frequency thumps and thuds because they just stop at 100 hertz. They don't go low enough to account for all that low frequency sound that is a big part of what we perceive. So the HIIC is easily measured as part of an IIC test because it's within that same frequency range. And therefore, it's also easily calculated from previously measured IIC test data. And I've done this at PAC. I've gone back to all of our 20 years of acoustical testing for floor ceiling assemblies. And I've taken that data and I've calculated an HIIC rating from it, because the HIIC rating is just a calculation standard. It's not a measurement test standard. And the HIIC rating is very useful for evaluating flooring and underlayments. Usually when we add flooring and underlayment to an assembly, the changes that we see in the impact sound levels are at these higher frequency ranges, really this range from 400 to 3,150 hertz. And that's why that range was selected. So we can use the HIIC to better differentiate between different flooring and underlayment combinations. It also works for evaluating ceiling isolators, so sound isolation on the other side of the assembly. The LIIC is a little different and a little more troublesome. So can't always be calculated from previous IIC test data because it's outside that range of frequencies that are measured for an IIC rating. And a lot of times, the data that's reported and what the labs will measure stops just at 100 hertz. They don't go lower than what's required for the measurement of an IIC rating. LIIC ratings are rarely affected by flooring and underlayment. Carpet and pad would be an exception to that. Of course, there are some exceptions to this that I'm sure folks on here could point out. But generally speaking, flooring and underlayment don't do much for the low frequency impact sound. So the LIIC isn't particularly helpful for evaluating flooring and underlayment, but it can be very helpful for evaluating ceiling isolators and other changes to assemblies as well. LIIC ratings are hard to measure, or harder to measure, because of their low frequency range. And because of that, they have lower accuracy and precision in terms of their measurements. And there's unknown and at this point probably fairly low correlation between labs. So what that means is if you take this assembly and you measure it at this lab, and then you build that exact same assembly in this other lab, you might get pretty different LIIC ratings. There's also unknown and probably low correlation between lab and field measurements. So if you get this sort of a LIIC rating in the lab and you go measure that same sort of assembly built in the field, there might be big variations between it. And there's a lot of things that go into that. I'm not going to get into all of that, but just know if you see LIIC ratings, you got to take them with a serious grain of salt. And that's not to say that they aren't useful. The most useful way, the most helpful way for LIIC ratings right now is to compare tests that were done at the same lab. And so that's something that I've tried to do with our data is, test different variations of an assembly, maybe different sealing isolators, things like that, at the same lab, in the same test setup, so that you can see those changes in the LIIC ratings, and those are helpful, and those can be good design tools to figure out how to improve LIIC ratings in whatever assembly you're working on. And speaking of improving, let's get into methods of improvement. So flooring and underlayments, right? This is a common way that we look to try and improve impact sound, right? So in this case, I have this example of an 18-inch open web truss. It's got 3/4-inch gypsum concrete on it and a resilient channel for the sealing isolation. And so you go from a bare gypsum concrete to flooring and underlayment on it. And you can see that the IIC rating goes up significantly from 43 to 55. The HIIC goes up even more, right? That's that bigger differentiation between flooring and underlayments. So it goes from a 41 to a 63. So you get a big 22-point improvement. The STC rating goes down a point, but that's really within test variability. Flooring and underlayments really don't affect your STC ratings. And the LIIC rating went down 3 points. That's maybe a significant change, but like I said, there's less precision to those low frequency measurements. And so you might see some changes down there with flooring and underlayment, but you're probably not going to see too much. So sealing isolators is another way that we look to improve acoustical performance, right? So in this case, we've got the same base assembly, and the only change is that the assembly on the bottom, we've added some additional rubber isolators to the resilient channel to improve the isolation that's provided at the ceiling. And so you can see here, the STC rating went up, but only by a point, so really negligible change there. But the IIC, the HIIC, and the LIIC ratings all went up by significant amounts. And just a note, especially for the acoustical consultants on here, the STC ratings, this comparison is limited because of flanking limitations at the lab. Believe it or not, even as we start to get up to just STC 60, we start running into contributions from laboratory flanking. Another way that we can improve the performance of an assembly is adding mass. We do this a lot when we add additional layers of gypsum board to a wall, for instance, to improve our STC ratings, or we go from 1 to 2 layers of gypsum board on a ceiling. But you can also see it here just, increasing the thickness of a concrete slab. And adding mass will typically improve all of these ratings. Your STC, your IIC, and your HIC and LIIC ratings. Insulation is another way that we can improve our acoustical performance, right? If we have a wall with no insulation in it, that cavity between those two hard surfaces, right, becomes sort of this reverberant space. Sound can build up in there. And if we put insulation in there, it can reduce that buildup of sound and improve the sound transmission loss through the assembly. Same thing works for floor ceiling assemblies. And so you can see here by adding insulation to this assembly, the first one has no insulation, and the second one has 3.5 inches of bad insulation stuck to the bottom of the subfloor. We get improvements in all of our ratings. Now, something to look out for here is like, okay, well, if a little bit of insulation is good, why not put more insulation in there? Why not fill the entire cavity? That can improve your acoustical performance, although like with a lot of things with acoustics, once you've made one step in including an element, increasing that, so like increasing the thickness of your insulation, you get sort of incremental gains in performance, not just like this big gain. But the other thing to look out for is a lot of the places where we're looking at acoustics, we're looking at sound isolation between spaces like apartments and condominiums. We have acoustical requirements, but we also have requirements for fire ratings, right? That's very important. And a lot of times our designs for fire are dictated by UL fire-rated, fire-resistive designs, right? And a lot of those say that if you increase the insulation thickness above 3.5 inches, you have to change your channel spacing and you have to reduce your channel spacing. So increasing the insulation thickness might improve your acoustics, but you have to reduce your channel spacing, which might reduce your acoustical performance. Or if you forget to change your channel spacing, you may have an assembly that's actually no longer fire rated, and that would be a very bad situation. Two other things that you can do to improve the acoustical performance of an assembly are stiffness and damping. And I don't have examples of those because they're things that can just be a little bit harder to test in the lab. So, but what stiffness would be, there's a project that we were involved in, a condo project, where it was steel C-section joists, and for whatever reason or reasons, the joists that were installed were under-designed for the span. And so the assembly was very flexible, and they were getting a lot of complaints about noise. There are other reasons besides just the stiffness that were causing the noise issues, but that was part of it. So they went back in and actually sistered in additional joists to stiffen the assembly. So you can, looking at the stiffness of assemblies can be a way that you can improve your acoustical performance or improve the benefits that you get from acoustical isolators. Damping is another way. So damping is sort of resistance to motion. And if we think about a car, right, as we're driving down the road, the springs in our car are the isolators, right? They help the wheels and tires move independently from the rest of the car. So the wheels take the bump, but we don't feel it inside the car. Damping is the shocks, right? So if we just have a spring, and you've probably all seen somebody driving down the road that has blown shocks or something, and they go over a bump and the car just keeps going up and down and up and down, right? That's because the springs have no resistance to that movement, right? So they'll just keep going back and forth oscillating. The shocks provide damping, so resistance to that motion. And we can add damping to structures in different ways. There's damped gypsum board panels, and there's other ways of adding damping, and there's probably some folks on here that get into really crazy tune mass damper systems for, high rises and things like that. So that can be a complicated subject, but just know that it's there as a tool sometimes. So in conclusion, code requirements, just baseline, right, within the building code for multifamily sort of spaces, STC and IIC 50. And there are, of course, acoustical requirements for lots of other spaces. For hospitals and schools and office buildings, there's either acoustical requirements that might be a regulatory requirement that you're obligated to meet, or there may just be recommendations and guidelines. STC and IIC ratings have their limitations, and sometimes those limitations can be significant, especially with IIC ratings. And in large part, the exclusion of those lower frequencies that really better indicate the thumps and thuds that are often the most annoying and obtrusive sounds. HIIC and LIIC address some of those, and they can be good design tools when we're trying to select assemblies that perform well so we can make quieter spaces. Ceiling isolation can improve both your HIIC and your LIIC ratings. The code requirements are minimums. If you're designing condominiums or luxury apartments or something like that, places where people are going to have higher expectations for the level of sound isolation, you should be aiming for something above the code minimums. And again, with the current level of performance specified by the building code, a large percentage of people are highly annoyed by noises from their neighbors, leading to reduced quality of life and possibly the negative health effects. And really, the health effects of noise are significant. It's a big thing. There's a big body of research about it. Fortunately, a lot of it is done in Europe and outside of the United States of America, but it's really something to pay attention to. And I think that noise control and quiet are big parts of creating, healthy environments, healthy spaces within the built environment.